Good morning, everybody. Oopsie. Henry says hi. That's why I wanted to show. I look like absolute shit today. I feel like absolute shit today. I'm getting over something, the plague, and just my face being absolutely dominated by the pollen in the air. Probably both. But Henry wanted to say hi. Oh, I'm sorry, Hen. Sorry. Want to say hi? Yeah, she says hi. Okay. I am excited about this particular um topic. Slideshow. Oh, oopsies. Because we're going to talk about the anthroposphere. And obviously, when I first started this class, I mentioned I don't know what I'm going to do for this module, and I was going through and um, I was inspired by sort of climate change. It relates a lot to climate change, but it's more of a direct effect and impact onto some of the different spheres and different systems that we have, and less so about the science of climate change and greenhouse gases, which we talked about in the last module. And you watched that really great documentary that Leo had. So it's related to climate change, but we're going to talk more directly about some of the effects that humans have had on different spheres, including human alteration of the geosphere, water use and modification of the hydrological cycle, biodiversity loss and ecosystem alteration, and this concept that is the Anthropocene, and geologic markers of human activity, which is how I got inspired to build this particular module. Um, the Anthropocene was a term that was coined, I think, in the 80s, if I'm not mistaken, by scientists who were like, you know, regarding geologic time, each one of these epochs and ages are distinguished by different fossils and different biological events that have taken place in our geologic history. So, how do we define our particular Holocene, Quaternary period, Holocene epoch as something dominated by humans? So, they've coined this term the Anthropocene, and it's a period that is defined by human dominance over Earth's systems. Um, it depicts the last 11,000 years, 11,500 years, that we have been in the Holocene epoch, began at the end of the last glacial ice age. So, yes, we're technically still in a glacial period. We're discussing the ice age over modern continents. Our last glacial maximum, if you recall from the cryosphere module, was 20,000 years ago. But the glaciers and the actual ice sheets that covered Earth that don't pertain to Greenland or Antarctica um, disappeared about 11,500 years ago. So that's the Holocene epoch. It's when we've seen rapid expansion of our population, of human population, and the development of modern civilizations. Intellectually, we're the most intellectual species on this planet. And because of that, we have experienced this mass expansion of society, which is great, but we've sort of gone about it the wrong way. Again, here's geologic time, and we are just in bloop, this little section here. If you remember, when you did the history of humans, and you did let's condense geologic time into a single calendar year, humans have only been here for about 2 minutes of Earth's history if we condense it into a calendar year. So not very long. And we've already done so much to this planet. So something that really inspired me was when I took sedimentary stratigraphy in my college undergrad career. I had an amazing, incredible professor. She won a bunch of awards for her work. And my class, so the class sedimentary stratigraphy, was all about literally just sedimentary rocks. It was a whole class dedicated to sedimentary rocks. And one thing she mentioned was, in 20,000 years, when more humans, if we've survived or whatever species comes through and is the new intellectually dominant species, when it comes through and we're digging through stratigraphy, um, to listen to the stories that geology tells, then they're going to find a layer of rock that has a high amount of hydrocarbon in it. And that hydrocarbon can be traced back to human plastic use. So essentially what this literature, this article is saying is the geological cycle of plastics and their use as a stratigraphic indicator of the Anthropocene. It's going to be our version of an index fossil. Um, we are essentially right now in this moment depositing a layer of plastic in our sedimentary history uh, that future scientists will find and say, oh, that layer of rock has a high level of hydrocarbon, which are plastic. We're going to have microplastics in this layer. That they can find under microscopes. They're going to have to analyze, and they're going to find a high level of these hydrocarbons as our NLCane indicators, as our biomarker indicators. We're effectively laying down a layer of plastic right now. That is our stratigraphic story. It's the same as the Grand Canyon laying down, depositing this layer of limestone, depositing this layer of shale, which tells us, oh, this used to be an ocean environment. But instead of us laying down really cool stratigraphy, we are depositing plastic. And that inspired me to talk about this module. Um, so not only are we impacting it with plastic, but we're doing a lot of other things too. We're gonna go through, and this one is geosphere. So I'm gonna not dive. I'm going to touch gently on environmental geology, including mining. And something that was interesting to me when I got into this field was when I first got into geology, there were really three career options I could have taken. And I got really lucky to find the fourth career option with just a master's degree. Um, that is my dream job, and I love it, and that's teaching geology. Otherwise, my career options were working for oil, working for mining, or working in environmental consulting as a geologist, and I honestly didn't want to do any of this. So I got really lucky and have my dream job now. Teaching you guys about all of these really cool things. So mining is the first anthropogenic impact to our geosphere, to the Earth sphere. And that is because, we find these metal deposits within our geosphere that we use as humans in some capacity or another. A lot of metal deposits are these fancy uh what's the word? My brain is cottage cheese today too. I don't want to say pure metals. It's fine. It doesn't matter. I'll think of it in a few. But they might be like gold, they might be silver, they might be platinum, precious metals. Oh my God. Precious metals. That's the word I was trying to think of. But they also might be metals that we use in our phones, in our computers, which are also really, really important. So mining is an important part of moving our society forward. But there are a lot of hazards and problems associated with this process, as you can imagine. This is just sort of an overview of how we find these deposits and what we do with these deposits. And essentially, once we find that metal or that ore, we call it an ore. I got a lot of students in my 101 class. I was like, oh, this sounds a lot like Minecraft. And I was like, oh yeah, I guess that's so if you've played Minecraft, maybe some of these some of these words are familiar, and ore is one of them, right? So you're mining ore in Minecraft. Um, and these ores are sort of a mixture of metal and rock. And we extract these metals from this rock in a couple different ways. We might crush them into tiny, tiny sand-sized particles so that the desired compound can be isolated. And this is actually a really interesting process. I've done it a few ways. If it's a metallic and magnetic substance, you can actually do what's called magnetic separation. So you have a magnet that you drop this sediment onto, and it will separate the magnetic particles from the non-magnetic particles. You also might have a density separation where some of these compounds are significantly more dense than the rock. So if you find like nickel, which is pretty dense, and you want to extract that nickel, you crush it in tiny sand particles, and then you put this into a substance that the nickel will sink to the bottom, but all those other rock particulates will stay at the top. So there's a lot of ways to separate these materials, and they're not cheap. That's the problem. So here are some of the environmental risks associated with mining. Mining itself is the loss of natural environment. We're destroying a lot of ecosystems by doing this. As you mine these precious metals or these other particularly sought after ores, you might have to work around other ores that have toxic substances. A big one is mercury. Another one is arsenic. These are naturally formed elements in Earth systems that are close to gold or close to silver. Actually, copper is a big one. So copper, there's a lot of copper formation down in the Southwest, Arizona, New Mexico. We have a lot of copper-based minerals that form down there. But along with those copper-based minerals, we also have arsenic-based minerals uh, and mercury-based minerals. And if you're mining through that to get to the copper, you might throw some of that contaminated dust into the air. People will breathe it in. It's not fun. Asbestos is technically a rock. So the rock, ooh, what is the rock? Well, asbestos is the way that that mineral forms, which is the like fibrous texture. It's really pretty, but the fibrous texture is very glassy and very sharp. That's what asbestos does. If you breathe in asbestos, it's just like essentially cutting your lungs up into tiny, tiny little bits with these tiny little glass particles. It's terrifying. Um, so anything that you're doing to get to this pure metal, this precious metal, you're gonna put that dust into the air. People are going to breathe it in. It's going to get into our water systems, um, our drinking water, our food, waste rock storage, obviously finding a way to deposit waste. I really thought about adding the Hanford site into this topic, but I, again, already have so much to go over. And the Hanford site was essentially not rock storage, but us dumping contaminated radioactive material into the ground that then affected the local ecosystems, including our farmlands and our local water sources. If you want, you should look into the Hanford site. It's very interesting. Maybe I'll bring it up next module when I talk about locals. Probably not. I won't have time, but look into the Hanford site. Tailing storage. Um, Again, this is after we've extracted material and you dumped it aside, dumped aside the stuff that you don't want. Uh, Smelting's a big one. Smelting it's actually a really cool process, and we've been doing this as far back as human history knows. So in the Iron Age, if you're familiar with the Iron Age, which I don't know when that was, I'm a geologist, not an anthropologist. Um, but the Iron Age of people, it was named the Iron Age because that's when we started smelting iron. And what we did was we found these rocks that had a high amount of iron in them, and we would heat them to a temperature where the iron would melt. The iron has a different melting point than the rest of the rock. So the iron would actually melt out of that rock and leave behind just the iron, and then we'd toss away the rock. So we would just have that iron, and then we could use that iron to build swords and build armor, and do all these other really cool things with this new metal that we've discovered within these rocks, which is how the Iron Age became the Iron Age. But the problem with that is that in this process, especially if you're doing a huge quantity of this smelting, it releases huge toxic particles into the atmosphere, and a lot of greenhouse gases as well. And leaching of metals from smelter waste, called slag, blah, blah, blah. But it's a really cool process, at least scientifically. It's really interesting because these different materials within this rock have different melting temperatures. I just think it's super fascinating. But it's really bad environmentally. I'm not going to dive too hard into this. Dive, because we're diving into the ground. It's the end of the term, y'all. Um, but it is a schematic of an underground mine, a modern underground mine. I've definitely been in like the historical, oh, let's go look at an old gold mine and it'll be fun. And it is fun. Uh, but it's very different than a modern mine, and safety wise, it's set up very differently, and we don't have those cool carts that we then push back. And we do have carts in a regular mine, but this is what it looks like. Here's the ore. This is the ore body that we want. And we have dug into the ground these different levels for us to extract this ore. You can look at it if you want. But you can see, I guess the big picture here is you can see how much space and how much of the geosphere we're affecting just in a single mine for one single ore. We have thousands of these around just our country, our own country. So hold on. Oh my goodness gracious. Hold on one second. Sorry, I had to blow my nose and nobody wants to see that. Okay, so this this also inspired me to do this particular module because I think it's a really fascinating topic. And it's currently, this is one of our huge global discussions that we're having right now between um, environmental groups and mining groups. So these are sea nodules. And I guess they're called polymetallic nodules. They're at the bottom of the ocean. There's a bunch of them at the bottom of the Atlantic Ocean that we found, and there's a bunch of them in the Pacific Ocean. And they form naturally. They form over thousands to millions of years, depending on the size. So this might be a baseball size one, which is awesome. And it probably formed over the span of millions of years, just sort of rolling around on the bottom of the floor. Um, these nodules contain a fuck ton of cobalt, nickel, copper, manganese, and other rare earth elements. And that metal goes into our phone. That's my baby. Goes into our phones, goes into our computers. It goes into our any electronic device that you have in your home, electric cars. So this metal is super, super important for our societal growth. Now, we're talking about different ways to extract these nodules, to mine these nodules. And they're at the bottom of the fucking ocean, right? So the mining process for the bottom of the ocean is very different than a mining shaft in like the Colorado Rockies, where there's a lot of gold, the Alaskan Aleutian Islands, where there's a lot of gold. Um, this setup is very different than the mining process at the bottom of the ocean. And there are a couple ways that, we as a global society have been talking about mining these nodules. This Belgian company developed a robot to scoop these nodules from the bottom of the ocean floor. And honestly, in my opinion, this is the best way to go about doing this. We're disturbing as little ecological systems as possible by using this robot, right? We're still affecting ecosystems. We're still scrounging on the bottom of the floor. However, this process is time consuming and thus very expensive. However, it does save us ecologically, or it's the least ecologically impacting process. The other process, so I learned about this entirely from this amazing woman. Her name's Diva Aman. She was on one of Will Smith's Nat Geo documentaries. Ooh, what was it called? Hold on, I can look it up right now. Called Welcome to Earth. I wrote it down this time. Which is on Disney Plus. It's a great series. I watched it. It was good. Will Smith is not my favorite person, but I do appreciate all these really rich dudes in Hollywood bringing attention to these uh, climatic and environmental issues. So she was shown on this show, but she did a talk in Seattle a couple years ago that I went to, and she talked about this process. And one of the things that scientists are talking about doing is literally taking a giant fucking net and scooping the bottom of the ocean to collect these nodules, which would be faster, it would be cheaper, but it is going to destroy the deep sea, bottom of the ocean ecology, and any ecological systems that form at the bottom of the ocean. And there are so many. So mining this product, it has been sort of uh, it's been said that yes, this is going to happen. We need this material. Funnily enough, all of these metals that we need are also found on asteroids. So we are also talking about the concept of mining asteroids, but like the cost of that is stupid as well. So people are like, well, we have this metal on Earth. Let's just mine these. And there are a couple ways to do it. And the more expensive and time-consuming way is better for the environment. Um, but we're in a world right now that might not agree that taking our time and spending all this money mining it is economically worth it. I also made the point that octopi lay eggs on these sea sponges. I think this is a sponge, or I thought it was an anemone, but this might be a sponge. that grow on nodules. Here's one of these nodules. Again, they're not very big. This guy's probably a baseball size. They range from baseball to smaller. They're not very big. The other issue is that small countries really rely on these resources. So there are some countries that want to help in this project and are putting in their own resources to help mine this material. Um, and so they want the cheaper option, right? Because they want the better economic system, which is the cheaper it is to get, we can sell for a higher price, we'll get a bigger profit. Um, oh, and then the metals extracted from these nodules we find in our phones. So mining comes in different ways. And environmentally, historically, it has never been a good process. And humans want instant gratification. We want the least, uh, the fastest option and the cheapest option. And environmentally, those two don't normally correlate. Okay. Another issue that we have is concrete. Um, so 4 billion tons of concrete are used globally each year. Cement is essentially 80% calcium carbonate. And if you don't remember what this is, calcium carbonate is limestone. So we mine limestone for cement. We also have this gravel bed that we, or sorry, this gravel mine, gravel quarry that we are mining clay from. So the cement is 80% calcium carbonate, which is limestone, and 20% clay, which we get from these gravel quarries. And then we also use these gravel quarries for like, I don't know, if you walk outside and you walk over some gravel. I am going to go on a walk later today. I might die, but I'm going to go on a walk anyways. And it's all covered in gravel. My pathway. Oh, hi, sweetie. Are you coming down? Where are you going? What are we doing? Oh, okay. What are we doing? You want to just say hi? Where are we going? What are we doing? Okay. So we get that gravel from a gravel quarry. However, we have to heat this mixture to 1450 degrees Celsius to get, what do we want? Where do you want to go? You want to get on the desk? Okay. We have to heat it to 1450 degrees Celsius, which is fucking hot, to get the calcium silicate compound that we use for concrete. And in that process, CO2 is released into the atmosphere. Um, Concrete, I'm not going to make you dive into this diagram. I had to look at this diagram when I took atmospheric sciences in my undergrad, and it's so confusing. He made us measure out the actual budget here. Concrete, cement production is by far the most significant anthropogenic production of CO2 in our atmosphere, and it has to do with how much we have and the CO2 that is released as we process it into calcium silicate. It's fucking bonkers to me how much concrete we produce. Oh, we're trying again. Okay. You just tell me what you want. So here's the fossil fuel anthropogenic emissions. We have coal, oil, and gas, but cement production is by far what? The biggest production that we have of CO2 emission. And we mine other minerals too. It's not just precious metals and limestone for cement and these nodules at the bottom of the ocean. Sodium chloride, we mine a bunch of used for melting ice and roads, softening water, seasoning, obviously. Potassium chloride, we use this as a fertilizer. Potassium's a really great fertilizer. There's an industrial fertilizer, it's potassium dihydrogen phosphate. Okay, and she's gone. Gypsum is a main component of plasterboard, drywall that we use in construction. And then marble and granite are quarried and mined for different uses, including countertops, stone floors, headstones. Um, so we're mining material constantly. And it's not, I mean, we have a finite amount of these resources, right? That's why they're called, well, they're not fossil fuels, but they're not all fossil fuels, but these are finite. We're going to deplete these eventually. And in the process of mining them, we're releasing a lot of greenhouse gases and a lot of dangerous toxic material. All right, here's where I get into fossil fuels. So there are several types of fossil fuels, but all of them involve the storage of organic matter in sediments or sedimentary rocks. That is carbon. So organic matter in sedimentary rocks is carbon. Um, Ultimately, this originates from the carbon dioxide that we've taken out of our atmosphere millions of years ago during photosynthesis. So photosynthesis, right, removes carbon dioxide from the atmosphere and releases oxygen. But then imagine, so that carbon dioxide goes into a leaf, goes into a plant, and then that plant dies and is buried um, very quickly. That carbon dioxide that was once in the atmosphere is now buried in the earth just as straight carbon, and it turns into coal. It turns into oil. And us releasing that system back into the atmosphere at a rapid pace is what is causing our carbon dioxide to increase substantially very quickly. So the big ones are coal, oil, and gas. I'm not going to read all of this. You can read this. Um, but coal, we're going to talk about significantly next week. And then oil and gas. Oil is obviously in liquid form, gas is in gas form. And all of these we release back into the atmosphere. And if you're not familiar, fracking is actually a super controversial process. If you've heard the word fracking, but you're like, I don't fucking know what fracking is, it has to do with really or with retrieving gas from. Do I actually do a slide on this? I might have a slide. Oh, I do. I do. Okay, so I'm not going to talk about it. Or I'm not going to read this, but it has to do with removing gas from sedimentary rocks. So here's coal. Again, we're going to talk more about this next week. But what I have implied, and this is just a really good depiction, is these plants around a swampy, stagnant water that is low in oxygen. There's not a lot of moving water. Moving water is going to have a lot of oxygen, but this is stagnant water that is a swamp. Um, and this dead matter kind of falls into the bottom of this water, and it doesn't decompose entirely because it doesn't have enough oxygen. And then over time, you get sediments that deposit over this peat, over this organic matter, this dead plant matter, making it even more compressed and unable to decompose. Over more time, you get it to turn into lignite coal. It's useless. Lignite coal is super useless. But the more time you spent, the more the more sediments that build up over that coal turns into bituminous coal. This is the coal that we use as a fossil fuel. So that's how coal is formed. Um, Migration of oil and gas. I'm not going to talk too hard. Hi, about this. But we have oil and gas that are built similarly to that of oil. It is just the burial of hydro. Oh my God, so dramatic today. Of hydrocarbons in our sedimentary system, and then we have these rocks that are formed over them that are impermeable. So, oh, oh, I thought I had a picture of an oil mine. I guess not. But I will say it's a similar idea where you have oil in a system and we build actually hold on. Okay. So I just wanted to show you oopsies, these pump jacks. Um boop boop boop. This is a pump jack. This is how we retrieve oil. So um it's a hydraulic system in which we pump down I'm trying to think of a good metaphor. So the system that we're pulling from is airtight, right? So we're not pumping air into that system, but it's the same process of like, I guess like, oh gosh, like sucking liquid out through a straw, right? We're pulling up this material through this process, through this hydraulic process, and we're retrieving this oil from impermeable formations where this oil is stuck. This is actually a depiction of fracking. So fracking again pulls gas from impermeable stratigraphy. Uh, through a similar process. And oh my gosh, fracking actually produces seismic scenarios. So like, um, this is actually an issue in the Midwest where we're fracking a lot. We're collecting a lot of gas, methane. Um, oh, there's another gas that we collect a lot of that I can't remember off the top of my head. We collect a lot of this gas. And in the process, we get these seismic processes, and the Midwest experiences earthquakes. And they're like, what the fuck? Why are we getting earthquakes in the Midwest? And a lot of it is fracking. I won't dive into the details here, mostly because I don't know all of the details of fracking. I'm going to have to learn when I teach environmental geology next year. But it's environmentally unsound because as we frack, we're inducing seismicity. What do you want? Come here. Ow. Hold my face. What do you want? She keeps walking across the screen, but I don't know what she wants. As we're collecting this methane and we're inducing these earthquakes to help us retrieve this methane, we're not only releasing it into the system, we're humans, we're not perfect. It's releasing it into local ecosystems. And if there's any type of water, this is an aquifer, which means that there's going to be a little bit of water here. It might release that methane into the water. It's going to destroy that marine ecosystem eventually when it makes its way out into a river system. It's not an environmentally sound process. Okie dokie. Oh, I'm also not going to dive too hard into this. You can read this. This is just a summary of what are the implications of resource extractions for the Earth and Earth's systems. And it was just a summary. So read through this. This is probably the material that I will put on the quiz. Some of it. Another issue regarding the geosphere that I really contemplated talking about, but ultimately was like, yeah, this is going to be really important, are our landfills. We dig these giant pits, and there are standards in which at least the US has regarding how we move our trash. Um, and this contributes heavily to greenhouse gas emissions because so we dump all this trash, right? And a lot of this trash is food. A lot of this trash is material that bacteria are then consuming, and this bacteria that consumes the products that we waste release methane. Oof, I'm dying. Release methane into the atmosphere. Huge amounts of methane. In fact, significant. This is our methane budget, and most of our, I guess not all of it, methane, oh my gosh, methane still comes from fossil fuels, and livestock significantly, but landfills and waste are a huge component into our methane budget. Um, the when I was looking into, okay, well, what are some good solutions regarding landfills? And the answers aren't helpful, unfortunately. We can't burn waste. If we burn waste, we're just going to release more carbon dioxide into the atmosphere, right? Um, Burying waste is like burying our problems. We can't bury them. And actually, if we bury waste, that's going to produce toxins into our ground, into our agriculture, and into our groundwater. And so these solutions were like, well, just use less plastic and compost. And it's like, cool, thanks. I can't compost in my apartment. I don't know about y'all. And I use as little plastic as possible, but ultimately, the issue does not come down to individuals. In your homework this week, you're going to look at your own ecological footprint. And it's hard to look at um, because, here we are sitting around thinking, oh shit, I can do so much more to help the environment. And I'm just going to tell you now, we can't really, but it's also not our fault. And I want you guys, in the last module, I asked about your climate anxiety as well. And I want you guys to understand that individually, it is not your fault, and it is not up to you to solve these issues. It is these multi-billion-dollar corporations that produce so much plastic and so much carbon emissions that then sell us these products. But if that's all we have in the stores and that's the cheapest option, and you are a family of five and you're trying to save money, the problem comes down to these giant corporations who could easily come up with greener solutions to sell us at reasonable prices, but aren't because they want the cheapest solution to make the highest profit. So take a breath. It feels really overwhelming at times, and I know that. And I teach this topic understanding that a lot of people stress out over this issue that we have globally. But take a breath, do what you can, but just know that this doesn't fall in your hands, and just vote the best way that you can to vote into office people that will help ultimately change um, how we work with corporations and how corporations thrive on capitalism and blah blah blah. And that's my soapbox for the day. But take a breath. I know this feels overwhelming and this feels like the end of the world, but it's not. It's really not. Okay. I don't know how long this video is already, and I apologize. We're gonna jump into hydrosphere and biosphere. Actually, hold on. I'm gonna blow my nose again, and then I will do it. Okay, okay. Sorry, Henry's now trying to. I don't know what she wants. Impact on our hydrosphere and biosphere. I love this topic. So, this is an abandoned ship that has dried up on the Aral Sea near Aral, Kazakhstan. And I like showing this image because so Kazakhstan is in the Middle East, and this was one of their major water supplies, but it was a very salty body of water, and this was just how humans have impacted the hydrological cycle so much that we're drying up oceans, which I shouldn't be happy about. It's not a happy scenario, but it's very fascinating to me that this is as much impact that we have had in on this planet. Groundwater, which we've talked about, so I'm going to just slide through here. I took this from my water module, but again, groundwater forms in these pore spaces in our soil. And that makes it permeable, and that is how we retrieve our water. That's how we get our drinking water. Here is our local watershed. So this is the Salish Sea. We're going to come back to this next week when I talk about local systems, but I wanted to show you it as a whole. Our Salish Sea consists of this whole waterway. This is the Puget Sound. This is the Strait of Juan de Fuca. This is the Strait of Georgia. But our waterways also come from these mountains, right? And any of the water and snow that forms on this mountain will then form these rivers, lakes, and streams that come down into our watershed. So this is the Salish Sea watershed. This is the Columbia River watershed. It's fucking massive. So all of these waterways, all the way from fucking Pocatello. I'm sorry if you're from Pocatello. I'm about to shit on your hometown. Pocatello is gross. I've been there once and I will never go back ever again. Idaho Falls, Twin Falls, Boise. This is the Snake River. It comes up through Lewiston, Clarkston, also gross. This is Pullman, if you've been to Washington State. So this is the Snake River. And all of these rivers connect to our Columbia River, which eventually go out into the Pacific Ocean and through Astoria. Why did I bring this in here? So the water demand of an area is a function of the population and other uses of water. The US uses approximately 3.3 trillion. So this is 3,300 billion, but if we just take this away and make it a 3.3, it's 3.3 trillion gallons of water per day for in-stream use. So this is water used but not removed from a river. But which essentially means like we use this water as part of irrigation systems, right off river systems, dam systems, if we put a dam on the river. But we use 410 billions of gallons a day for off-stream use. This is thermoelectric power. This is irrigation. This is public supply, our drinking water, our showers. This is industry. And then 100 billion gallons a day for consumptive use. This is a lot of fucking water. We use a lot of water every day, which we get from our water tables, which goes into our groundwater. So that is that system. This is a really cool graph of agricultural water use. Oh, go away. Domestic use and industry use. The other interesting thing to note is how much we extract versus how much we consume. We use a lot of water. Eh, well, okay. So I brought this slide in, I guess. The formation of a cone of depression of the water table. So the issue that we're having in terms of our groundwater is that we're depleting our groundwater so much that we actually have to lower our well systems to be able to extract this water. And depending on who's using the most amount of water. So here we have one well, one well, one well. But in terms of this agricultural system who needs more water, they have this well buried in our water table, which is how high the water comes up in our groundwater. And if they're using the most amount of this water, they're going to dig deeper and deeper and deeper to be able to extract that water. But we might have independent wells that dry up because our table is becoming lower and lower and lower. So this is a really interesting depiction of if we're pumping water from our ground for specific uses, other people might not have access to that water, even though they're on that water table. And this is happening primarily in the South. We're very lucky. I feel very lucky that we live in a heavily precipitated area, where our water table is relatively, I don't want to say consistent because it's not consistent, but we get enough precipitation in this area, that I'm not necessarily ultimately concerned about our water usage. However, there are areas in the South that are not as privileged as we are here in the Northwest. And as a country as a whole, we don't have as high water stress as we do with other countries. That being said, this is a map from 1995, and this is a map from this year. In 1995, water stress for us was 20 to 10%. So this is water stress is defined as having a high percentage of water withdrawal compared to total available water in the area. This means that we were withdrawing a lot of water versus how much water we actually needed. But now it's 40 to 20%. This is significant. And then you can see that areas in the Middle East, and Southern Asia, are in considerable danger from not having enough water, not having enough healthy water for the people and the populations in this area. Mexico's, and then it's just the country as a whole, but the Southwest is getting pretty fucked too. Okay, hold on. I'm gonna pause one more time because okay. I wasn't sure if I needed to dive harder into that, but I wanted to preface with that information because now I'm going to talk about an issue that we're having right now. So drinking water is always going to be an issue, and globally it's I talk about this in my environmental science class, and I go hard into it in my environmental science class, regarding water inequity and how many of the countries, especially in Africa and the Middle East and Southern Asia, experience a lot of water-related health issues, and ultimately water-based deaths because of water inequity around the world. And one of the modern issues that we're seeing, are these giant fucking data centers that guzzle power. And we have a few in Washington. But it's not just Washington that is dealing with this. And the biggest issue that I've ever seen, not ever seen, that feels really dramatic, that I have personally seen is I went down to Arizona, I don't know, 2 years ago, and I saw these data centers. So if you've never seen a data center, actually, hold on, they're fucking massive. These data centers are centers for like Google, for Amazon. Amazon has one. I don't know what this one is. Data center. Any of these huge fucking billion-dollar corporations has these data centers, and this is where they store information. This is where they store all of the data that you could possibly dream about, and they look like this on the inside. There's these server rooms, so they hold thousands of servers. that contain all this information. There's generators, but the biggest issue are these cooling systems. And they can use air, but generally they use water to cool the server room. You coming up? And the way they do that is they filter this water through a tube system that ultimately cools off um, these servers as they're being used by humans in online as we're typing in information. So here's what some of them look like. Oh, maybe not. Okay, we'll come back to that. So ChatGPT was a big one, and I did a whole seminar. I went to a whole seminar that talks about this, and one of the issues with ChatGPT is that ChatGPT has 200, oopsies, I missed a zero, 200 million active users. I use ChatGPT all the time. Um, we average approximately 8 chats or questions a day, but it only takes 20 to 50 questions to generate 100 milliliters of wastewater. 100 milliliters is, well, here I have my little pepper. It's like this much. Okay, that much water. It's not a whole lot individually, but 4 ounces of water for 50 questions and the amount of people that are using ChatGPT a day equals about 1 million gallons of wastewater a day. This is where we're putting a lot of our fresh water. So I wanted to make it clear that a lot of these data centers need space geographically. They want to find somewhere that's cheap to build this giant fucking building. And they want flat land. So where are they finding most of this space? In the Southwest, where temperatures can reach upwards of 90 degrees on any given day. 130 degrees in the summer if you want to be stupid. That's a lie. 130 is like Death Valley, but 110, 120 degrees in the fucking summer, which means that they're going to need more water to provide coolant for these systems. So I'm going to turn off my heater too. And they put it here. Oh my God. My life's a mess, you guys. It's a mess. Okay. So imagine we have all of these systems using all of this fresh water. And the problem with the Southwest is they don't have a lot of readily available water, right? They live in the South, they live in a fucking desert. So they're getting this water from other sources. And getting from other sources means that they're depleting that water for other people. And one of the biggest issues that we are seeing is in California, Southern California. A lot of these industries, including these guys, but also like food industries like Nestle, are taking water from Southern California who need this water, people who need this water, and are taking it for these giant corporations, these giant industries. Sometimes even just selling it back as water, Dasani, or any of your bottled water. They're taking from areas like Southern California and places that don't have enough readily available water because it's cheap and because they can. I'm sorry, I'm on a like power-induced soapbox here. My other big pet peeve is I took this picture of Mesa, Arizona, where I went a couple years ago for funsies. I don't know where I'm at geographically. I was like up here somewhere. Maybe you will look at, so let me take a step back. Mesa, Arizona is a suburb of Phoenix, Arizona. Beautiful area. And it's also very cheap to live there. The houses, I mean, cheaper than here, I guess. So a lot of wealthy individuals have winter homes down here. I don't know if you can tell where I'm going with this, but these wealthy individuals in the winter like to fly down to Arizona every weekend and stay down there. I used to work at the country club up in Bellingham, and many of those individuals who are members of the country club had houses, had not summer houses, pardon me, had winter houses in Mesa, Arizona. And they would fly down. It was a cheap flight from Bellingham. It was like $200 round trip to get to Mesa. And it's a straight flight from Bellingham. So they would fly down and they'd stay every other weekend in their comfy little winter house. And as you can see, one of their hobbies is golfing. And golf courses require a lot of fucking water to maintain. There's like 5 golf courses here, you guys. I don't even know how many there are. And this is a really big problem in the Southwest. Are these rich individuals who come in? Oh, and there's some over here too. Look at that. Are these rich individuals, these wealthy individuals who come in to these communities and they want to golf. And so they maintain these golf courses for the wealthy individuals. The wealthy individuals are putting money into these golf courses. And then all of a sudden they're in a drought. And um, you know, middle class, lower class people can't afford drinking water, can't afford to bathe every day. And yet these golf courses are remaining maintained and nice and very green. So where is our water going and why is it going to some of these areas? And it all has to it comes down to wealth disparity. And ecologically, it's destroying a lot of marine and river ecosystems, but it's also very detrimental to human populations. So there's my chat GPT. So what other impacts do we have on our ecosystem? Sorry for my water rant. Oh, it's going to get worse. Don't you worry. Um, if you've ever seen these storm drains, I want you to know that it doesn't, I mean, maybe you already know this, but these don't go through a filter. These storm drains go directly to our oceans, go directly to our streams, which then lead directly to our oceans. And so here we have stormwater runoff that has oil from cars. Another big issue, especially in the wintertime, is salt. If we're salting our streets, that salt will run off into our stream waters and effectively contaminate our streams, our creeks, our rivers, which we get our drinking water from. And a lot of it is industrial salt, which is more than just NaCl. A lot of it has that potassium and it has dihydrogen phosphate. Um, and so we're contaminating ourselves by contaminating the streets that then run off into our storm drains. Agricultural runoff is also a big issue. So this is a creek that is next to a bunch of cows, and cows like to poop like everything else. And they'll poop into on the ground, but that ground or that poop will seep out into our streams. Obviously, they're probably pooping directly into the creek in this scenario. One of the biggest issues, and we study it at Skagit. I know we just did a student showcase, and there was a student who did a report on this in the environmental conservation program. Is dog poop. Ugh, you guys, this is my biggest pet peeve. And are you ready for my biggest soapbox that you will ever see? Listen, I love dogs. I love dogs. I don't love people. And I especially hate entitled dog owners who leave dog shit and think, well, it's just part of nature. This is fine. So not only does dog shit um spread bacteria to other dogs, to humans, to other animals. Parvo's a big one. There's some other really big uh, dog-based bacteria and dog-based diseases that are being spread to other animals because of this situation that people are just completely oblivious to. And it makes me so angry. But the biggest one is fecal coliform bacteria. So this is a bacteria that's very small and it's in dog shit. And mind you, these are dogs that we have oh my gosh. See, words are just so hard today. That we own as humans, right? So they have been, oh my goodness, hold please. This is so embarrassing. I literally thought of the word right as I paused. Okay. These are animals that we've domesticated. We are feeding them processed foods. They live with humans. So they have different diseases than wild animals. And one of these is fecal coliform. Fecal coliform, if you leave your dog shit out in just out on the ground and let it disintegrate and decompose into the ground, it's going to seep into our groundwater. It's going to seep into our river systems and eventually out into the oceans. So not only is this going to affect humans, it's the bacteria that this is very small, and it's very difficult to filter out of our drinking water. So not only is this going to affect humans and it's affecting wildlife, right? at least terrestrial wildlife. This is significantly affecting our marine wildlife, like heavily, because marine wildlife has filter feeders. These are filter feeders. These guys filter out everything that they get in the water and they eat the plankton that they're able to sort of filter through that. These are blue mussels, Pacific blue mussels. These are Pacific oysters. These are butter clams. I think they're butter clams. These are clams. I don't know if they're butter, if they're the other one. It doesn't matter. More blue mussels. So these are all species native to the Salish Sea area and they filter out the gunk. They're actually really impressive creatures. And we're using these as we have gardens. We'll grow them as quote unquote gardens. Because if we have thick, opaque water and we put oysters, we put clams, we put mussels in this water, they actually filter out that opaqueness, turning the water clear again, making it really, really important for our local ecosystems to see the water, to swim through the water, to fend off predators, or to see food. So these biological entities are so important for our marine ecosystems and for us, that if we're putting dog shit in the water and thus contaminating it with fecal coliform, these guys are going to be affected, and they are. We're actually finding that their reproductive cycles are being disturbed, and we're finding that they're not able to build as strong as shells because of this bacteria, because of this fecal coliform bacteria. And there are so many other organisms that eat these shellfish. Sea stars eat them. Sea stars move really slowly, so they eat what they can catch, and they catch a lot of shellfish because shellfish don't really move. Otters eat them. Octopi. I love octopi. They're my favorite. And these guys will eat shellfish all the time. And if they're eating this bacteria, it's actually going to build in their systems, and they're going to get sick, and it's going to affect their reproductive cycles. It's going to affect their ability to thrive in these marine systems. Um, Ecologically, this is just an ecological system where we start with producers. We have primary consumers, secondary consumers, tertiary consumers. And as we go up in this ecological chain, we have what we call biomagnification. So imagine you have this toxin that could be fecal coliform bacteria. It could be oil. It could be a microplastic. Doesn't really matter. And you have all these tiny little flies or these producers or even just primary consumers, the very bottom of the food chain, effectively, that are consuming this toxin in some capacity. They might not be consuming a whole lot of it, but if you go up in the food chain, the things that eat these are going to need to eat a lot of these to be able to thrive, to be able to survive, right? So they're eating a lot of this. So that toxin is actually getting higher and higher in concentration in something like the bluegill. And then the bass that is then eating this bluegill has to eat a lot of bluegills, which means that that concentration is increasing thus far. And then imagine us. We're at the top of the food chain. We're eating all of this bass. We're collecting this bass. We're consuming that. We're consuming the toxins that this bass has produced. So if you've ever heard like, don't eat too much seafood because of the mercury, that is biomagnification. The bioaccumulation of these toxins over time is going to get bigger and bigger through the food web. So biomagnification is consuming this toxin through the food web and how this toxin is magnified at higher trophic levels, at higher food chain levels, because of how much we have to consume. And bioaccumulation is just the slow buildup of these toxins over time. So biomagnification specifically, we're consuming more based on where we are in the food chain. But over tens of years, if we're consuming this consistently, that's the bioaccumulation of this toxin, and it's going to be in our body. That's how we get cancer. That's how we get really, really sick. That's how we get diseases all of a sudden out of nowhere that are like, where did this come from? So this is a really big problem. And dog shit is by far my biggest pet peeve. Pick up your dog poop, people. Just pick it up. It's not hard. And for fuck's sake, don't leave it in the bags on the walking path for other people to deal with. Just don't. Just pick up your dog shit. It's not hard. If you have a dog, it is your responsibility to pick up your dog shit. And I have full on yelled at people for this. And boy, I've gotten into some steamed arguments with strangers about, oh, I'm sorry, do you have a dog bag? Your dog just shit over there. Do you have a dog bag to pick that? Oh, no, I don't have one. Do you have I don't have a dog. Why would I carry a dog bag? I need to start carrying dog bags actually for this purpose. Um, I full on got into a yelling match with this woman who was like, oh, no, I don't have a dog bag. And I was like, why do you have a dog? If you don't have a dog bag to pick up your dog shit, why do you have a dog? Well, why do I have it? Just pick up your dog shit. Pick up your dog shit. Yell at people. Be aggressive, people. Okay. Another issue considering biomagnification, we're going to bring it all the way back to the start of this lecture, which was like 3 hours ago. So sorry about that. Are plastics. So the plastics that we are producing, they don't decompose, right? They're a hydrocarbon. They're built of hydrogens and carbons. They don't decompose in our system. Instead, they just break down into smaller and smaller particles. And we call these microplastics. And this is a huge component of biomagnification. So uh, biological entities will consume these plastics. Um, hold on, let me figure out where I'm going with this topic. Um, if this is that toxin that I talked about in biomagnification, they consume these plastics and they biomagnify through the food chain over time. Now, here's the thing with plastic that people get really confused and really sort of mixed up about. Plastic is not necessarily toxic. It's not poisonous. If you consume it, you're not going to go into like cardiac arrest and die. The issue with these microplastics is that they're a nutritional filler. So imagine you consume a piece of plastic. You're going to be full. You're going to be like, well, I don't need to eat. I just ate this delicious piece of plastic that was sitting here, styrofoam or thread, whatever. Styrofoam is actually a huge problem with microplastics because they're fluffy and they're big. So you're consuming these things, but they don't provide any nutritional value. So these organisms that are consuming microplastics are not getting the nutritional value that they need, but they're feeling full. So they're actually dying of starvation, or they'll die of starvation before they're able to consume actual food that provide nutritional value for their bodies to thrive. So we're biomagnifying this microplastic, and we have found microplastic in breast milk now. We found microplastics in organs in our systems. We're finding microplastics just about everywhere. And the problem, again, is not that they're necessarily toxic. They're definitely going to be problematic if, we're finding them in like organs and tissues. But the fact that we're finding them in breast milk is particularly troublesome because we're effectively then feeding our children these non-nutritional filler that's going to starve our children. So the more that we build into our systems, the less nutritional value, the less nutrition we're going to be able to provide to our children. And it's the same situation for any other organism on the planet. They're consuming these plastics and they're not able to provide their body what they need. And we don't know that we're doing it, right? We're finding this. I probably have microplastics in me now. I'm not doing it on purpose. I'm not taking a chunk out of my my plastic material that I have hiding in the house. This is just happening and accumulating over time. This is the big problem with plastics. So they start at the bottom of our food chain and they're working their way up. And there is and one of the biggest problems and locations that this is taking place in is our oceans, right? There's a mile-long, mile-wide radius floating island of garbage in our Pacific Ocean that has accumulated. So we're around this area, I guess this here. And if we continue to grow at the rate we're growing, we're not growing linearly. This is this is a type of graph called exponential. We are growing this plastic, not growing this plastic, but we are adding to this plastic problem at an exponential rate. So by 2100, we're going to have 520.1 cubic meters of microplastics in our oceans. This is a problem. This is a huge problem. Okay, so this is part of our marine hydrosphere anthropogenic impacts. The other issue that we're seeing, which comes back to our filter feeders and our clams and mussels, are nitrogen and phosphorus. Humans agriculturally wanted to find the cheapest and easiest way to grow plants, as we do, right? And to do that, we add fertilizer to help that process. And those fertilizers contain nitrogen and phosphorus. In fact, earlier this year, I grew crystals with my Geology 101 class, and we used this really cool salt called oh boy, uh, nitrogen dihydrogen phosphate. I might have just pulled that out of my butt. There were a lot of chemicals as part of that, but it's an industrial fertilizer to help plants grow. And that's because nitrogen and phosphorus are what we call a limiting agent. So plants need different components to grow and they need carbon dioxide, they need light, they need water. That's all part of photosynthesis, right? But one of the things they really need and they really like are nitrogen and phosphorus, which are part of soils. So they get these nutrients from the soils, but they're the first nutrients to run out. So as soon as nitrogen and phosphorus runs out, that's as much as they're going to grow. So humans thought, okay, well, let's add nitrogen and phosphorus into the soil so that they can just keep growing and growing and growing and growing, and it's not going to limit the amount that they can grow. So we add nitrogen and phosphorus to our tilled soil, to our agricultural processes, so that our plants can go really big, so we can get as much yield from that agriculture as possible. However, when we do that, we're putting so much nitrogen and phosphorus down that we're also, when it rains, all of that will run into the groundwater, which runs into our system, which runs into our stream system, which then runs out into our oceans. You can see where this is going. So this nitrogen and phosphorus then sits in our ocean. Well, we have plants in our ocean too. We have algae in our ocean. And in fact, algae produces the most amount of oxygen in the for the planet. It produces 75% of the world's oxygen. And algae is really important, but algae also really likes phosphorus and nitrogen. And so when we get this nitrogen and phosphorus, this algae is like, fuck yeah, this is awesome, and it will just explode. This is called a HAB, a harmful algae bloom. Because this algae is just like, yeah, I'm going to take all this nitrogen and phosphorus and I'm going to explode. And then all of a sudden, you have all of this algae that's covering the surface of the ocean. When it does that, so it does a couple things. First of all, as it explodes, it's consuming a bunch of oxygen. Um, uh, Hold on, let me make sure I'm. Oh, no, it's not consuming oxygen. I apologize. During photosynthesis, it consumes carbon dioxide and releases oxygen. However, when that algae dies, and algae does not have a long lifespan, I don't know, a week or two. When it dies, it sinks to the bottom and decomposes. And when it decomposes, it actually consumes oxygen as it does that. Here we go. Decomp uses up dissolved oxygen in a bit. When it does that, the fish that also need that dissolved oxygen to breathe, or the crabs, or the other plants, then can't live in that area because there's no oxygen for them to breathe effectively. So when it decomposes, it takes in all that oxygen. It makes it a dead zone in our oceans. Also, I want to point out that when this algae is thriving at the surface of the ocean, it blocks light into this region as well, which makes it really difficult for any of our benthic plants. Yeah, benthic plants to grow. So this algae bloom is doing a couple of things. It's restricting the light to the bottom of the ocean, but it is also taking in a bunch of oxygen as it decomposes and dies, creating these dead zones. So this is why nitrogen and phosphorus runoff into our oceans is super problematic. We might also get red tides. Oopsies. Red tides are sometimes when we get nitrogen and phosphorus, but other toxic substances in our algae. It's not always red, actually, but sometimes we get this red coloration. And then again, our filter feeders are filtering through this algae, trying to find the yummy food that it needs to thrive. And that is really toxic. That is really poisonous. And so these clams, these shellfish are dying. And if we go clamming at that time, I don't know if you've ever gone to the beach and you see a sign that says red tide, don't go clamming. It's because you're about to eat really toxic algae from these clams, from the shellfish. And I don't know if you've gone regularly, but over the years, I've seen more and more of these signs pop up more and more frequently. So here are the dead zones. We have one here in the Pacific Northwest, but they're significant along the East Coast and along the Gulf where we have a lot of agriculture. Same with Europe here. I think this is Japan. Any place where we have a lot of agriculture, we're going to see these dead zones. Oh, thank God. I was like, how much longer am I going to go? You poor people. You can watch this on 2 times speed, but you're still going to watch like 4 hours of this. I'm very passionate about this, okay? Oh, sorry, Hen. So next week we're going to talk about the Salish Sea and our local systems. And I wanted to bring this image in. This is just our local tribes and our local First Nations people that lived in this area that inspired the name Salish Sea. Um, and I will talk more about this next week. So, anyways, that is our show. I'll stop sharing. And I know that was a lot. And I know this sort of dived into a lot of environmental science, but I think that environmental science and geology are very hand in hand. And I mean, that's why I started studying geology in the first place was to better understand, um, sort of the anthropogenic impacts of uh, of geology and earth science. So I'm gonna stop recording. And oh wait, now I'll make a different video for the homework and lab, so you don't have to keep watching this. Okay, bye.